So, we resume our afternoon session with the talk of Elmar Diederichs. The title, you can see, is the development of non-Gaussian component analysis.
Thank you very much for the introduction, and thank you, sir, for the invitation to give a talk here about my stuff. And what I want to talk about today is some recent developments in non-Gaussian component analysis. And the topic that non-Gaussian component analysis is dealing with is the following situation. So what we understand if we talk about structural analysis is actually a cloud of set that contains some information that is embedded in high-dimensional memories. And what we're actually looking on is some projection or some subspace that contains only the informative part of the complete data density, and we try to project out the uninformative noise. Of course, the requirement of every such method would be that we try to reconstruct or extract every feature that contains information in data without losing information. So to get this, to state this more formally, we have the following problem. We have some high-dimensional data in an Euclidean space of dimension d. We consider an IID data sample, and we assume that d is large across variables. For simplicity, all data should be normalized. And we assume that Gaussian components, as usual statistics, are informative, and we are only interested in the non-Gaussian components, so it means we try to take all the data in some suitable, choose non-Gaussian components. The requirements for any acceptable statistical method in that sense will be that we do not use any a priori knowledge about the data density, and it would of course be nice if there will be no dependency on the second moments of the Gaussians or other unrealistic assumptions on the data density. So this is more or less our setting that we try to cover. The model that we use in all developments that are up to now given in the non-Gaussian component analysis use this semi-parametric assumption on the data density. So this rho is actually the data density, this phi is the density of the normal components, q is some nonlinear smooth function, and t is the operator that projects the data on the non-Gaussian components. So consequently, the non-Gaussian subspace, or the subspace of the informative components, can be defined as the kernel, as the orthogonal component of the kernel of t. So we see that we have a linear method, and the goal is to estimate projector on the non-Gaussian components without estimating the model parameters.
Can you tell us?
Sure.
So does that integrate? Is that the density rho?
Rho is density.
So you assume it integrates to 1?
It integrates to 1.
I mean, it's like a fact, or it's normalized about it.
No, this is an assumption. So if this assumption is valid, so there's something to do in structural data analysis. If this is not true, then okay, you're done. Nothing to do. Nothing to be extracted. So there's no important informative in the data. Okay, so how is it possible to recover some elements from the data space? So we have some lemma that gives us the possibility to do this. We assume that rho is the data density, and we of course assume that the semi-parametric assumption shown on the last slide is valid. And we use this smooth function phi. So phi actually can be every function. But we see that different variants in non-Gaussian component analysis will differ exactly in the construction of phi. So if we assume that, then we can show that if this element beta of phi, defined as the expectation value of the gradient of phi, is an element of the non-Gaussian component subspace up to an error that depends on the covariance matrix of the data density, not of the empirical covariance matrix, but of the covariance, real covariance matrix, and the expectation of this product. Moreover, we can show if this condition, the product of x and phi expectation of that, is not zero, then it is exactly part of the non-Gaussian component subspace. So this lemma actually will be used in more or less all variants of non-Gaussian fault analysis. And the question actually is how to make effectively use of this lemma in algorithm.
I'm not sure I understand the lemma. So,
Yes.
so what's going on? So I choose psi.
You choose psi. So I will explain later how you can choose psi, and there will be many advantages and disadvantages depending on the method, how you choose and how to construct psi. So
Okay.
this is decisive.
Fine. And then what do I make? Like, what's my assumption on psi?
The assumption of psi is very weak. You only assume that some regularity conditions hold. So that means that psi is smooth
Okay.
and derivatives existing and are also smooth. That's all. That's all you need.
Okay.
But implicitly, you're assuming that the expected value of x against psi of x is small, right? If you want to get something that's meaningful.
Depends on some situation. So typically, the expectation value of this product is not small. So if it is not zero, then it's sure that you have some kind of error of the estimate, or some kind of error of psi as a function, as beta is a function of psi with respect to beta that is definitely chosen from the target space.
So,
Well,
if you take any psi that is even, the expectation of x psi of x will be 0 by definition.
No, so if you choose that by
No,
definition,
because they have the third moment.
okay, so the question now is how can we make use of this setting? And in order to construct psi from the data, we will construct psi as a sum of some test functions HL. And the test functions actually, well, they should only be smooth and be informative with respect to the distinction of Gaussian and non-Gaussian components. And we define additionally objects, gamma L, that is some kind of representation of the noise appearing condition from the last lemma, and the information bearing vectors eta L that are defined by gradient, expectation of the gradient of the test functions. And we assume that there are some error bounds on these empirical estimators. So what we can prove also is that the estimation of these objects can be done up to an error bound. N is the number of the samples of the data set, and D is the dimension of the data space. C only depends on the total test function. So there's sometimes some discussion about the real or best choice of H. So actually, for the theory, it's not decisive how we choose H in fact. But numerically, we will see there are some differences that are not so small. But I will explain that later on somewhere on some photos. Yes, please.
In the last equation, D is the dimension and N is the number of samples.
Right.
So you don't need many more samples than dimension, I guess.
Yes, of course. So the method is of course designed for the fact that the number of samples is much larger than the number of dimensions of the data space. So in the other case, the whole is a dimension.
So what is C? So just before the lemma, you have the max over C. What's the dependence in C? How does the sum depend in C? I'm assuming C is the vector of CLs, right?
C is a vector of the component CL, that's right. So we could assume here that we have convex combination of test functions. And I've introduced some error bounds that I will use later on some later floors.
So gamma hat and eta hat are going to depend on C, or
They
because
depend on C, of course. I will show this on the next slide.
this is per L, right?
This is per L, that's right. So you construct gamma L and beta L independently of HL, and of course, if you combine them in convex combination, you have an error bound that depends on C. So C is the vector of coefficients.
But where is it on in this thing? Is it in where is it? Like you're maximizing over C, but you don't have a function of C. I'm just confused.
Yeah, that's right. So I have introduced it a little bit too early. But we'll see it on the next slides how these objects will contribute to our method. Okay, so basically there are three different approaches to structural data analysis using non-Gaussian components. The first of these approaches comes from Diederichs, and he constructs the decisive functions of psi in the following way. So psi has this form, and the idea is that if psi fulfills this kind of condition, so this is our noise-killing condition from the first lemma, then the idea is to construct an element from the non-Gaussian target space by using the information-bearing component eta L and subtracting the noise. So the drawback of this method, of course, is that you have to compute it to study the high-dimensional inverse covariance metric. This is one of these things. So M, of course, cannot be estimated by this method. It has to be given a priori to the analysis.
What is M?
M is the number of the reduced space, of the target space. The second approach is sparse in some sense, because we again use a linear approach to estimate psi from the data, and we consider the convex production problem that's stated below. So we try to find the minimum over all coefficients that fulfills our noise-killing condition, and of course we want to have a sparse solution. So the idea is that psi actually is a randomly given vector, and if psi is not completely orthogonal to the target space, the solution of C's will give you some informative vector that is has not too much, or the deviation of this vector is not too much from the target space. So in this case, an estimated element beta L can be defined by using this coefficient CL from the solution of this optimization problem, and we can show that every such constructed beta lies in the vicinity of the target space, and the deviation can be bounded by square root of d and the norm of the inverse covariance measures. There's some constant c that only depends on d and the norm of the samples. The decisive drawback of this approach is that you have to choose some vectors psi that you project on the target space on the convex hull of these estimated eta L. And of course, this is not so easy. If you have no idea where the target space is, and you only have the choice to do this randomly, you will have, in the higher dimensions, with high probability vectors psi that are orthogonal to the target space. So this method will not be very efficient in high dimensions. So both approaches, this sparse non-Gaussian component analysis and the non-Gaussian component analysis from the slide before, have the same problem. They lead to some kind of random regression problem that you have to solve. That means you have a set of estimated elements beta from the target space, and you have to construct a basis from this set. So there are actually two possibilities to do this. One solution for PCA in the usual way, but the drawback of this is that if the estimated elements beta are not informative, so it is required that so the solution will be very volatile and very bad, and in order that the solution is nice, it's necessary that the eigenvalue m, so that m's eigenvalue is larger than L times epsilon square. Epsilon square is our error bound from the first lemma, and L is the number of test functions that we have chosen. So a different solution would be to use the Brownian ellipsoid, try to compute it, and the consequences of using Brownian ellipsoid is that the projector on the target space can be reconstructed up to an error of d times square root of d, and c there's a constant only depending on the eigenvalue, on the nth eigenvalue, and the error bound from the first value.
So will the dependence on number of samples?
In this bound, oh, I don't know exactly, there must be some, but it's not really here. I don't have it in mind. So it's, of course, it's inside of this constant c, but I don't know exactly.
Oh, it's in epsilon.
Excuse me?
It's in epsilon.
And epsilon is 2, that's right, because epsilon is our error bound from the estimation of the elements, but there's some influence of anything to this error bound, but I'm not sure up to now. Okay, now to illustrate the systematic product between these two steps of non-Gaussian component analysis, let's have a look on some kind of numerical illustration. So what's written here is I have plotted some non-Gaussian components in 2 dimensions, and the idea of the numerical simulations is to embed these non-Gaussian components in high-dimensional noise, and we try to reconstruct it by an algorithm. So the error measure that we use is very simple. So we assume that VI is the orthogonal basis of the target space, and consequently, this is our error measure. And what we observe is that comparing to other methods, exactly for other linear projective methods of dimension reduction, if you compare this to projection pursuit, the first variant from Blanchard non-Gaussian component analysis and this sparse non-Gaussian component analysis, we see that the convex projection approach to non-Gaussian components actually is a little bit better than other linear projective methods. So it's not true for all types of non-Gaussian components, but if you compare the behavior of the error measure up to higher dimensions, you can see that there's some kind of systematic progress. Well, this is not the end of the story. We can, of course, improve this. I have made some comparison of the method with respect to noise, and it's not surprisingly that the sparse non-Gaussian component analysis is more or less stable under noise, and the noise scaling range here is done in the following way. So we have deviation from normality that increases up to in a geometrical scale in this field. Other methods depend on the inverse of the covariance matrix, they depend on this. So the final approach to structural data analysis in our case is we can use also some kind of semi-definite approach. So this is introduced in a paper by Diederichs from last year, and to this end we have the same objects. We have some kind of estimators that are responsible for the noise killing and some kind of objects that are responsible for estimating the information in the data set. And we try to avoid any product vectors because we have actually no idea how to choose them with this, and the bad choice of the product vectors will actually lead to components, to coefficients that will not lead to informative elements from the target space. Consequently, we can avoid solving the Range-reduced regression problem, but instead we try to solve directly the following semi-definite problem. We try to reconstruct the projector pi directly from the data matrix U is built up from our estimate from our objects eta 1 to eta L. Under the constraints that pi is a projector on the n-dimensional target space, C is the vector for our coefficients, and this is our noise-killing linear constraint. This is a problem that we try to solve. Obviously, this is a hard problem. We cannot solve it directly, but we can maybe relax the problem in order to get a convex reformulation of this. And additionally, we will make a third step. Up to now, it's up to the dimension of 50, it was not necessary to use any kind of structural adaptation. It was not necessary to iterate the method in order to reuse the estimation result in the next step of, or in the next iteration of the method. But towards higher dimensions, it's absolutely necessary to make some kind of structural adaptation. So we make it in the following way. So we have some estimation result in the k-1 iteration. This is our projector. And we use this projector as a priori information for the directional sampling to improve the quality of the projection of the next iteration. So this completely leads to the following sequential procedure. We first of all have some kind of directional sample. We have some kind of directions where we project the data on. Along these directions we estimate or we compute our test functions, and from the set of test functions we construct the objects eta L and gamma L, and directly from this set of objects we try to directly estimate the projector from the data. And then we iterated the procedure, and if we only found a little bit of information in the data set, we can improve step after step the quality of the estimation. Okay, so the thing that we have to do is we have to relax the problem. How can we use it? So first of all, we translate this norm problem into a trace problem. And we make some kind of linearization. This is more or less standard. So we introduce a positive semi-definite metric as a product of the vectors and coefficients with rank 1 as a new linear variable. We relax the non-killing condition into this iteration formulation, and we drop the non-convex rank constraints as well as for the variable x and for the projector pi. We didn't use a rank constraint, instead we use a trace condition. What we get then is we get a relaxed and constrained set point problem of the following form. We have a trace of 7 matrices. This is the this is our, so this is not our projector, but pi actually is some kind of sub-projector, because the set of projectors is not a convex set. And in order to cope with this problem, we introduce a semi-definite matrix pi following, that fulfills the following conditions. Pi is semi-definite, the trace of pi is m. And this pi, actually we call it a subprojector. So then we get a convex problem that can be solved by some first order methods. And what we finally, so first of all, let's have a look on the estimation error that is that comes with the solution of this optimization problem. We have the following lemma, so we assume that P head is the optimal solution of the semi-definite problem, and we assume that pi star, so this is the real projector on the non-Gaussian performant subspace, is a convex combination of rank 1 matrices of this form. Of course, we have our noise killing condition, and we have starting formulation. So if this holds, we can show that pi head, so spanned by the first m eigenvectors of p head, with probability larger than 1 minus epsilon, it holds that the bound of the estimated projector now depends not on the dimension of the data space, but this is a systematical progress, but only on the dimension of the reduced space. So these are some bounds on the estimated element, and rho is the relaxed threshold from our noise killing condition. For the trace, we have more or less an analogous condition. And if we use a Frobenius norm, we can show that the pi head, the deviation of the pi head with respect to pi naught, is also bounded by the reduced dimension and not by the dimension of the data space. The condition, the constants C, a little bit technical, but they So what does it mean in practice? In practice, we have to introduce our linear constraints into the formulation of the semi-definite problem using some eigenvalue decomposition or some singular value decomposition. Actually, we know that the complete problem acts on the kernel of G, and if we use some eigenvalue decomposition of gt times G, we can introduce a submatrix Q that is built up by the columns of gamma. This is the orthogonal transformation matrix of the eigenvalue problem that corresponds to the mentioned eigenvalues of this product. So using the Q, we can introduce a new variable, a new matrix V, and we get some kind of regularized and hence unconstrained convex formulation of our final problem of the following form. Now, this final formulation allows us to solve the estimation of the projector onto the target space directly from the bottom. So let's have a look on what this means in practice. In practice, if you compare linear projective methods of dimension reduction, we find that the behavior of the semi-definite version of non-Gaussian component analysis is much better towards higher dimension than comparing linear projective methods. So, and the decisive point is that this is independent of the choice of the non-Gaussian component. So actually that means that the semi-definite reformulation of non-Gaussian component analysis makes a much better use of the estimated information than the other methods. So if we do the same comparison with respect to noise, we can see that independently from the choice of non-Gaussian components, we have a more or less independent method to noise data. This is of course a nice result. And if we have a look on higher dimensions, we see that the behavior of the semi-definite approach to non-Gaussian component analysis leads us up to, or gives us a chance to reduce the dimension of data sets up to, say, 150. Here the box plots go up to dimension 130, and you can see that at the end of, or towards higher dimensions than 100, the behavior of the method becomes a little bit, gets a little bit worse. So the number of the test functions L is increased superlinear. So the consequence is that the numerical cost of the estimation of the target space increase. So from my point of view, the method will close due to computational limits up to dimension 150. Now this is so my last final state, or the current state of non-Gaussian component analysis.
Thank you very much. Are there some short questions or remarks?
So, how many data points did we have for all these?
So typically I use 1,000 data points.
Okay. And B, can you quantify what is the cursor dimensionality here? I mean, or in a way, but that an exponential number of right, an epsilon net in d-dimensional dots has an exponential number of directions possible. So it's like searching for a non-Gaussian component.
Yes, I'm not completely sure. So what's the topic? So
can we quantify how many projections are we going to need, or
okay,
the complexity of finding?
Yes, of course. So
one non-Gaussian component.
okay, of course. This can be done. So the minimum from my point of view is that you need 10 projections per dimension. And if you
so linear.
Actually, it's superlinear because this only works up to dimension 50, up to 50, and then the increase is a little bit superlinear. So it's not quadratic, but well,
So basically, we need an exponential now, because the average projection is one of the square root of the dimensions. Okay, so you need a huge number of directions to find direct. This is actually, if you have a chance, okay, then this will work. That if you want to guarantee anything, you need an
Okay.
dimension number of directions. So,
Further questions?
More questions? If not, I think